joining us, the E-Waste Alchemist, Professor Sahajwalla. We're very honoured to have her here presenting her achievements at the Sustainable Materials Research and Technology Centre at the University of New South Wales. Now, when China introduced a ban on the importation of 24 types of solid waste in January 2018, the inherent inefficiency of Australia's $15 billion waste industry was suddenly exposed, and an annual average of 619,000 tonnes of Australian recyclable materials were left without a home. It meant our country was having a waste crisis. As founding director for the Centre of Sustainable Material Research and Technology, the University of New South Wales, Professor Vena is revolutionising the recycling science in collaboration with industry. She was appointed the director of the New South Wales Circular Economy Innovation Network, which brings together stakeholders from across government, industry, research organisations to develop new processes and supply chains for reducing waste and improving sustainability. In 2018, Professor Vena launched the world's first e-waste microfactory, where valuable metals are extracted from discarded smartphones, laptops, circuit boards. She now also wants to try and move this first e-waste microfactory into a global model. She's also won many awards. She was 2012 overall winner of the Australian Innovation Award. She's been a fellow and long-serving judge on ABC's television show, The New Inventors. She was also last year awarded New South Wales Australian of the Year. I'd like to introduce Professor Vena. Thank you.
Thank you. Thanks very much, Brett, for the opportunity to speak here today. I'll certainly want to acknowledge that, first of all, the Australian Research Council here in Australia that has over many, many years been supporting the research that we do, which means that the fundamental science really is the foundation of what we have to be able to do to achieve the kinds of outcomes that we want to talk about today. So if I may be able to get the ability to share screen, Brett, that'd be great. And I can then start to share my screen, but I'll give a little bit of a context to those listening. In the Smart Centre, or the Sustainable Materials Research and Technology Centre at UNSW in Sydney, Australia, is where we look at all the way from fundamentals to of course the translation, and that then allows us to effectively look at how we take that basic material science and to do that. So I have at this point in time, just to come back to you, Brett, I've got the slide deck ready to go. I've got my share screen
button down the bottom.
Yep, I've done the share screen, but it's not giving me access to share. So done all of that. I've hit the present at the bottom of the screen as per the advice, but I'll just keep giving a bit of a context as to what the Smart Centre does at UNSW, and of course the partnerships that we have with industry in Australia, supported through the Australian Research Council, allows us to take this ability to take all kinds of e-waste. So when we talk about e-waste, of course, as we fully appreciate the complexity of different kinds of metals and plastics, and of course a lot of rare earths that are present in, for example, hard drives, magnets, that are an opportunity to understand how we recover those valuable metals, and to really acknowledge the fact that we've got here the opportunity to look at how when equipment reaches a point when you cannot put it back into reuse, of course, all equipment becomes obsolete. How do you actually go after each of these different kinds of materials? So I guess from our perspective, what we want to be able to do is we want to show that it is absolutely possible to really look at how we can indeed show this work that we're doing here at UNSW. So hopefully everyone can see the screen at the moment. Let me know if you can see my screen.
That's perfect. Yep,
Okay,
perfect. Thank you.
excellent. So this is really what we're doing at the Smart Center, is looking at technologies, looking at fundamental science, and of course the technological innovation, which I'll talk to a little bit around micro factories, is really about ultimately, creating a whole new supply chain of materials that are going to come from end of life assets. When you do get to that point where it cannot be reused, of course, or become when assets do become obsolete, you need to be able to go back and understand the foundation of what we're trying to do here is about getting quality materials, so metallics to plastics, and everything else. But it's got to be materials that are fit for purpose if you want to put them back into its next life and future applications. So basically just giving you that bigger picture of what Smart Center is all about. We're doing those fundamentals of materials, not only looking at it from the context of recycling, but also looking at it from the context of their ability to be deployed in their lives beyond that first life. So if you were converting different kinds of products into new forms, new chemistries, new structures, what is the purpose of doing that? So, the fact that you might take even simple things, batteries, for instance, and they might look simple, but of course, as we know, really complicated in terms of the kinds of important metals that they carry. How do you then take those batteries that are no longer functional and go into those and go after some of those important metals like cobalt and manganese and zinc and so on? So these are the kinds of questions we're asking. But then, of course, when you do recover these important metals, you've got to bring them out into the right form and the right structure so that you can put them back into their next lives. But just to pause and reflect, as I mentioned about batteries, we do, of course, have these kinds of challenges across the world, but looking at the context here in Australia, what we have in Australia, of course, that was launched last year, battery stewardship, this BSc that is being run in Australia, that of course is now mandated with the charge to be able to set up schemes and systems whereby batteries are properly collected and systems are put in place. But if you look at the scenarios over the last several years, what we are seeing, and this is just some data from a few years ago, how much of this will end up in landfill in Australia. So certainly an opportunity there for us to do something about. But then if you step into the domain of applications with lithium-ion batteries, there are a whole range of applications. Of course, we look at not just IT equipment, but also all kinds of other assets. So it is important to understand that bigger picture context, all kinds of consumer devices that we know, and not to mention, of course, electric vehicles that are going to be coming into the pipeline, and whether they are rechargeable batteries or indeed some of the ones that are disposable. We know that they all, even in the lithium-ion battery space, so many different chemistries that are indeed available. And from our context, again, to be able to go back and say that it's not just about putting all the batteries together in one, grand smelter that's going to just smelt out magically all these important metals that I was referring to, like the cobalts and the manganese and nickel and so on, but rather to be very targeted and focused in on making sure that we are actually allowing those different supply chains of input resources, different kinds of batteries, so that we can get the best possible value. The quality matters, because of course the quality of what we then are able to recover from these kinds of assets means that it can go back into remanufacturing. So when we start to think about recycling, as we can imagine in these complex systems, it is very much about ultimately saying that it's not just about recycling, but we've got to go beyond those 3 hours of reduce, reuse, recycle, and start to think about that 4th hour of reform. We need reform because we know that these input chemistries are different, and therefore we're going to have to think about how we remanufacture these different kinds of elements and compounds. And of course, they might present themselves as oxides, for example, in those electrodes. So many different chemistries that we can go back and look at. And then when you come right back into the broader picture of all the valuable metals that are present in our waste batteries, you can imagine that the opportunity there is significant, because of course, again, as we are all starting to appreciate the fact that, as the world of decarbonization becomes more and more front and center of minds, people are looking at technological innovation, whether it's in industry or whether it is in mobility sectors, IT equipment. In all of these cases, the one thing that we do all have a shared responsibility is making sure that these kinds of assets, of course, have the best possible chance of getting those valuable metals out, because, of course, as you can imagine, that these are limited resources on this planet. And of course, if we are to do the right thing from an environmental point of view, from a human point of view, I think we need to keep in mind that both human-centered, technological-centered solutions are important, that they're all aligned. We can't simply say, well, it's okay to go about polluting the planet as long as we can get the best possible value out. We need to be able to have that alignment. When it comes to circular economy, it's all about not just keeping an eye on the economic value, as we can see there for these different kinds of metals, but also to be able to start to think about what do we mean by safe circular economy. And that is also extremely important, that all kinds of technological innovation looks at a holistic view as to how different kinds of businesses, for example, in the ITAD world, are going to be connecting to the value of these important materials, but to do it in a way that we recycle, reform, and remanufacture, whether we do that in the chemistry, whether it looks at metals, metal oxides, all these important materials that, of course, matter to us. And I'll come and talk a little bit more about the fact that it's not just about, of course, metals, but also about plastics. And again, these important considerations are there. So what do we actually mean when we start to talk about recycling and remanufacturing and looking at the bigger picture on micro factories? What we are really saying here is that these kinds of technological innovations when it comes to recycling and remanufacturing in micro factories can actually perform very targeted recovery. And that targeted recovery is important because you can then have multiple sites, different scales, different locations, and we can actually recover different kinds of materials that are then going to be fit for purpose for their future applications, because designs will evolve, technologies will absolutely evolve and change over time. And so if you are looking at these different solutions in different locations, you're able to offer these decentralized solutions for processing equipment and indeed getting the best possible value. So your recycling is now getting coupled with manufacturing of materials, and that's important. So it's just to hone in a little bit more in that detail that I was talking about. What are these different kinds of applications and chemistries and those compounds, whether it is, for instance, in our batteries, those materials that are LCOs, lithium cobalt oxides. You can see all those different kinds of chemistries that will keep coming to the forefront in different application scenarios. And this is where, of course, from our perspective, to be able to have an understanding of how do you then channel these different assets and different products into different kinds of supply chains so that you can go back and have different modular solutions. And this is what microfactory is all about, to be able to have modules that allow us these different opportunities. So let me give you one example here. I mean, what you can see in this particular slide is how we've taken, for example, lithium ion batteries and the kinds of materials that we have, both in the recovered cathode and anode powder. As you can see there, the powder, of course, as you know, gets recovered. We've got different kinds of metallic foils, copper foil you can see on the screen, as well as aluminium foil.
We're seeing we're not seeing the slide come up. You might need just on your screen to click on the icons on the left.
Oh, okay. Can you see the slides now?
I can see the slides. We're on slide 1 at the moment.
Oh, I'm so sorry. So you're not seeing the slides scrolling
No.
down? Oh, my apologies.
Yeah, sorry. Yeah, that's okay.
Yeah, look, I am just going to try and do this again, if you don't mind. Let me just start to present, and I will, because on my screen I can see it here, but I don't know why it's not scrolling through. So look, I can see
if
it.
you leave that screen there and click on the icons, because we can see that front page perfect. If you can just scroll, just click on 2, 3, 4, or 5 on the left-hand side.
Yep, sure.
And leave
I
the
can
screen
do
as
that.
is. Yep, perfect. Yep. Absolutely perfect. Thank you.
Okay. Yep. Not a problem at all. So I guess as I've sort of taken you through a bit of that journey, I'll just kind of point to some of these slides as we go through. So this is what I've been talking about with the Smart Center, some of the challenges with regards to lithium-ion batteries, different chemistries that I mentioned, and indeed, of course, to kind of hone in on some of the valuable metals and opportunities that exist. Talking about, of course, our microfactories and why they matter to be able to have those decentralized opportunities, so we can set them up at different scales and, of course, have very targeted recovery. So the slide that I was basically pointing to as I'm sharing it with you now is to be able to just show you how complex the structures are, of course, internally, when we do have, of course, not just the metallic foils that you can see on this picture up at the top, but also you can see the powders, the recovered cathode and anode powders. And of course, what that then means is that we're seeing, materials that are rich in different kinds of metals. So, where do you start with that complex mixture of this powder is to be able to then hone in and understand how do you go after, for instance, in this case, one of our technologies is about recovery of that cobalt. And you can see in that picture that you've got metallic cobalt that, of course, is able to be recovered from this kind of mass of different materials. Now, why that matters is because, as I was showing you before, different kinds of cathode materials, whether they are rich in cobalt, lithium, manganese, nickel, and so on, you can be very targeted and focused in how you indeed can recover some of these metallic streams at the right quality and the right chemistry. So this is what our microfactories are really all about. The kinds of systems that we have in place really allow us to then focus in on different kinds of metallic outputs. So if we were looking at, of course, a lot of these obsolete circuit boards, what we are developing are solutions to actually isolate those important metals. And of course, in a lot of these kinds of circuit boards, I wanted to just point to that important, question: why does it matter? So with this slide, what you can see is the concentration of metals like copper and tin on our printed circuit boards. Of course, the column that you see on the right-hand side, as opposed to the column that shows the concentration of these metallic materials that are present in our ores. Of course, the opportunity to look at our circuit boards as effectively, resources and valuable resources that are present in these highly concentrated forms. So, well, you might say, well, how do you then go after a lot of these important metals? What you're seeing on the screen, there's some of the technological pathways for micro recycling that we have developed from these printed circuit boards that then allow us to thermally micronize and produce these kinds of different streams. And the two examples that I've shown you on that screen there are tin-based alloys and copper-based alloys. Of course, to do that, you don't need to necessarily have one big smelter to smelt everything down. What you have got an opportunity here with these thermal micronizing technological innovations is to be able to thermally isolate these important metal alloys. And you can see that tin has been isolated at 500 degrees C, copper at about 1000 degrees C. And of course, a lot of the analysis that we have done to not only show that these kinds of technologies are feasible, but also importantly, what matters is the alloy and the alloy chemistry that we can then produce, and showing that you can then start to go after a whole range of different kinds of input boards, You can do that at the right scale. You can be very targeted and focused in the kinds of metal alloys that you can produce. So indeed, now when you look at some of these kinds of solutions that we're showing you on the screen there, what you can see is the opportunity to, of course, go after these types of technological innovation in a safe and a sustainable manner. So it's back to that important point around safety of circular economy, and that safe circular economy means you can get the best of both worlds, the economic value that underpins all of these important materials, and to do it in a way that we care for human beings and care for our environment. So what do we mean by micro recycling? Is what I've been capturing through these different examples, that we can recover copper and other metals. We know that, of course, micro recycling pathways, we can do that in a controlled fashion. We can, of course, look at the opportunity to not only go back and have a look at, of course, what we mean when it comes to different kinds of metals, but also equally importantly, as you see on the screen there, that we have also shown that it is possible to thermally isolate some of these rare earth oxides from our hard drives. So if I can explain to you in a moment what we're looking at here, as this is kind of scrolling through, you can see in the middle of the screen there an example of what we're doing when it comes to the thermal isolation at the micro level. What you can appreciate is magnets are rich sources of neodymium, in this case, and iron. How do you then take that neodymium and iron and isolate the two elements? And this is exactly what you're seeing happening in front of your eyes. The shiny droplets that are emerging through that, that dark matter in the middle. That shiny droplet is the metallic iron, and of course the gray matter that's then left behind. That, of course, is what is the rich matter in rare earth oxide. And that's important, again, to be able to appreciate that all kinds of complex compounds that we know are rich in rare earths are going to be present in complex compounds format. How are we going to effectively isolate the kinds of strategies and solutions, and scientifically what we mean by micro recycling is what is evident there in front of you in that video. So these are the kinds of new scientific advances that we are making in micro recycling. So just to be able to take you further along on that journey, what we have, of course, been doing is we've been starting to introduce that whole concept of fourth R, that fourth R concept that of course, as we can appreciate that when it comes to the complexity of e-waste, the simply relying on those 3 R's of reduce, reuse, recycle is not going to be important when you're talking about destruction of those assets. And you want to be able to make sure, whether it's your hard drive, that example of what we just saw, going right down at the elemental level, and really being able to show that that product has literally gone through the journey of being completely unmade. You've done that isolation at the fundamental level of those elements and compounds is important. So that now is really all about that fourth R of reform. We have reformed those kinds of elements. We've taken those end-of-life materials and transformed them into those fundamental building blocks. And that is important because then it can go back into further production and future lives of many of these different kinds of materials. And of course, one might say, well, okay, well, that's with the kinds of assets that we're looking at. But let's come right back to some of the basic elements that are present even in our battery systems, those humble batteries, zinc carbon batteries, many other disposable battery systems. They are rich in these elements that we've been talking about. For example, that zinc and manganese. But of course, you can't just expect that you're going to physically pull apart any of these systems and simply through physical destruction that we're going to go back and recover those important elements, because these are important compounds. And you can see in this particular slide there that, again, that dark matter, that powder that comes out from those batteries, in those materials, we've got various compounds. And of course, what that then means from our perspective is to be able to show that it is indeed possible to go back and literally unmake those compounds. So as part of the journey of how we destroy assets, what we are talking about, the journey of unmaking. And if the journey of unmaking is coupled with the journey of remaking, then we can be really clever in saying that every time these different kinds of materials come into our hands, we don't just see it as a waste. We see this as a brand new opportunity, and that opportunity to be part of that supply chain. So we think about circularity in a way that we're holders of assets, but we're also holders of valuable materials right at the in our hands. And if we're going to hold these assets, we need to recognize that inherently these are valuable materials. They can become part of feedstock for future manufacturing. And of course, all of these important elements can be put back into remanufacturing. So from our perspective, of course, a lot of these solutions that we're developing for micro recycling, and indeed working with our industry partner here in Australia, the kinds of things that we are doing. I wanted to show you an example of also e-waste plastics. As you can imagine, a lot of these kinds of solutions are real, absolutely. They are economically viable. The example of the economic argument here that we're making, that these plastic filaments that we are producing in our micro factory are of course highly valuable because of the fact that they're used as feedstock for 3D printing. So if you can imagine that we're focusing not just on the metallic side, but also on plastics, and really honing in on of course, what does it all mean? And you might say, well, of course, plastics are important, but they don't just present themselves in the hardware and the casing of our printers and laptops and all of that. There are so many different kinds of polymers that we may not have even thought about. Think about all those flexible circuit boards, that are there in so many devices. They don't just have copper in them. They also have, as you can imagine, these layers of polymers. What do you do with that layer of polymer that sits on top of that copper layer is an important question. That polymer layer is rich in carbon. So we've got another microfactory that allows us to then say your polymers, depending on the nature of polymers, you can actually go back and you can fundamentally deliver those materials and products. So in the slide that you're seeing in front of you, we're generating plastic filaments. So that's when a lot of these kinds of plastics that are there in your hardware can be converted into plastic filaments in our microfactories. And of course, they make perfect good economic sense to do so. These plastic filaments then become feedstock for 3D printing.
Just a quick question, Professor.
Yes.
Are you able to just give us a bit of an overview of the energy to recover all these assets versus the benefit of the assets, and what sort of research is done in relation to that? So the effort gone into what has come out, is that something that will obviously come with efficiencies in the future, but it'll be a question that could quite often get asked.
Yeah, look, absolutely. And I think one of the things that, we've got to bear in mind is that when we've got to do a like for like comparison, right? So if you were talking about, say, where does your copper come from? Copper is produced in smelters, obviously at temperatures, that exceed about 1,000 degrees Celsius. So what you're really talking about is, how do you then, in our instance, when we're talking about extracting both tin and copper, the fact that you can do these at temperatures that are fit for purpose. So, you're not having to then say, look, I'm going to have to transport everything to a copper smelter. So not only are you saving on and gaining efficiencies from reducing your mileage when it comes to taking your waste over long distances, potentially, all of that road mileage that you have to do, but also then come right back to the fundamentals. What is the temperature at which these different targeted solutions work? So if you are isolating tin, as I showed you in one of those slides, the temperature there is 500. You don't have to necessarily take that entire circuit board up to 1,000 plus degrees Celsius. if you're going to be isolating tin. You've already now gone through that process of one metal being isolated. What you're now left with is highly concentrated form of some of the other metallics like copper. So now we know that if you raise that temperature, still only 1,000, which is less than what typical smelters would be operating at about 1,200. What you're really then saying is that how I can now isolate these materials at relatively lower temperature compared to that baseline smelting operation. You come to the slide you see on the screen there with green manufacturing of plastics. Again, the question is, if your micro factories are like for like able to get high quality plastic filaments, for example, from those waste plastics, and do it in a way that you reduce your carbon footprint, you can decarbonize in a big way, because all that polymer that we're looking at is coming from 100% waste. So effectively, what you've done in that journey of decarbonization, you don't have to use any of the virgin materials. You don't need those brand new polymers to go back and make these plastic filaments. So that like for like comparison is to say, where would those filaments come from at the moment if they are being made where it's purely about using brand new resources, as opposed to, in our case, if you're making it from recycled content, you've actually saved on all of that embodied energy that you are effectively bringing in through that recycling journey. So that decarbonization is both the combination of that ability to take advantage of those materials that have already been made on this planet. And this is the key point. Then when we talk about recycling and remanufacturing, what we are doing is we are reducing our carbon footprint significantly, because we don't have to make those raw materials again. Those raw materials and all the energy that went into making those raw materials, whether they're metals or plastics or ceramics, all of that energy that went into it in the first place, we don't have to spend that energy again. We simply have to do recycling and remanufacturing. The question, of course, is with the complexity of all these parts and materials that are very closely integrated, whether it's a circuit board or whether it's a hard drives and magnets that are rich in rare earths. In all of these cases, it's not just about a mechanical recycling solution, but rather you have to be able to isolate, and this is why we call it micro recycling.
Yep. Now, Professor, I'm just a little bit also mindful of time, but there was a statement you made about 15 minutes ago, and that is waste to value. And I think that's probably something that resonated with me very early on, as my ears pricked up when you had that conversation, because what you're doing here is, and what I want to try to do with this presentation is that there's many ITADs, not only here in Australia, New Zealand and APAC, but in Europe and America. And no one is having the discussion that you've just recently presented, which is, okay, well, what does putting waste back into the ecosystem do? This will have to be inevitable in one day, because we cannot keep taking resources out and just throwing them back in. Organic, these resources are not organic; they need to be reutilized. But how can your vision and what the work you're doing be? How can our ITADs globally get to see what you're doing, or how can we get that message across? Because I think it's a very valuable discussion. That this is the first time I've heard it at this level, but I think customers need to understand it as we're talking about circular IT and sustainable IT. Where does it end up? And if this is the world leading in what you're doing and what you've achieved, we want to make sure that message can get out there and to the broader global community, not just here in Australia. So is there a way that we can engage or understand what you're up to?
Sure, Brett. Yeah, no, look, I mean, very important question, because I think, like you've picked up that key message that these are limited resources. And, we can't keep thinking about, equipment as if it's just got that one life, and therefore when it becomes obsolete, then, suddenly now it's too hard to recycle and remanufacture. And I think, to me, we do need to be able to say that for example, the kinds of scientific solutions and technological solutions we're developing at Smart Center. And if people are absolutely interested, there are a whole range of other technologies that, of course, I haven't had the chance to present this morning. But I think from that perspective, what we're really trying to do is build those connectivities. So, the example of the work we do with industry partners in Australia, like Kandui Technologies, like Renew IT, I think to me, that's that classic example of how the collaborative ecosystem can work. And yeah, if people want to have a look at examples of what we've deployed, have a look at our Smart Centers website. I think the successful examples really work when you've got the entire ecosystem collaborating and working together. So yes, absolutely, it could be your IT, service provider who's then looking at those assets where they can then be channeled back into remanufacturing. But to be able to have a fully transparent supply chain, that transparency is important, so that when somebody's, of course, kind of giving you that service to kind of recycle, remanufacture, or whatever it is that you want to do, I think to me the important question is to ask questions around the whole of life cycle, right? So you look at this particular example I have on the screen there with green manufacturing of plastics, coming from IT, equipment. Our industry partners are able to not only take that plastics, but manufacture those filaments, and then, of course, connect to end users who want 3D printed parts. So we're not just stopping at that point where we're saying, look, our responsibility is done. We've made these plastic filaments, so we're all good. We're taking it all the way into the entire circular systems thinking. And that circular systems thinking at the Smart Center really creates that ecosystem where there might be an end user who's super keen to have, manufactured parts and components that are basically made from, 100% recycled plastics. So it's an opportunity to connect with a whole broader ecosystem of industries. And that's exactly what we're doing here in Australia. And certainly a lot of these examples on our website, where the ability to then take those plastics, create those filaments, and put them back into production. So all of the metallic alloys, you could make potentially the same argument. If you created these micro materials that I was showing you, those little tiny, drops of metallic outputs, they're absolutely going to be a key for 3D printing of metals. So I know I've focused on 3D printing of plastics, but you're going to have to recognize that all parts and all components in the future, when we start to think about our supply chains, are going to rely on access to feedstock, whether they are plastic filaments or whether they are micro materials of metallics that I've been presenting. Those metallic micro materials are then going to become feedstock for 3D printing of indeed complex parts and systems. And that agility that any manufacturer will need is, where can I access high quality alloys? Because every time you want to redefine what that alloy chemistry is going to look like, you need to be able to know where to access it, not just, a copper smelter that might make bulk alloys, but rather those niche micro alloys that we're talking about in this particular case. Producing those niche metals is going to be absolutely key. And this is what we do at the Smart Center, is to really hone in on some of the high quality materials. And I think the work we're doing with Renew IT here in Australia is something that we're really proud of. That collaboration and that partnership is key to demonstrating the points that I've just been talking about. We want to be able to make sure that, our industry partner, and in this case, if I use that example of Renew IT, is also got the capacity and the will and the desire to be part of that technological advancement. So the fact that we can set up a micro factory right here in Sydney shows that collaboration is, going to deliver real world outcomes. And these are the kinds of micro factories that we're going to be setting up at Renew IT, whether it's for our plastics, whether it's for our metallic materials, but to do it in a form that allows us to produce these micro materials so that we can take it to that next level of remanufacture. And that ecosystem of what SMART and Renew IT's collaboration is. Let's put the materials back into the ecosystem, prove that the performance of what we produce is also at par and at the world's best standards. So that's really what that is all about. And yeah, I'd encourage people to look us up on our website.
Fantastic. Look, thank you so much, Professor, for your time. I know you're extremely busy. I've learned a lot in this session because I have not thought about the ecosystem in the way you've just presented it, and I'm going to be having a chat with James later on to find out how he's worked with you, and thank you, James, for helping set this up from Renew IT. He's a sponsor here. So thank you once again, Professor. Have a great day, and we appreciate your time, and I'm sure the audience learned a lot from today, because I know I did. Thank you.
Thanks so much for having me.
Thank you very much.